Thank you. When I noticed that I was going to be following Mark and Professor Panda, it's a little bit challenging in 20 minutes to give something that's more insightful than what you've already seen. So what I decided to do was give you a little bit of Cray's perspective on how we design and build systems that are of the highest scale. And looking out, typically we look out 5 years at Cray. We're often involved in procurements with the government or various entities where we're looking out and we're asked to project. But Exascale is a whole other beast. Projecting out 10 years and looking at the technologies that we might have in play is something that really taxes our limits. But I wanted to give you a little bit of perspective on what we try to do in that domain and why we think we might have some insights with respect to Exascale. Our view at Cray is that we're most interested in productive systems. We don't typically bid for large-scale installations of one-off technologies. We look at every single technology. We ask ourselves, is that a technology that can map to the wider community of HPC? And this is even more important in Exascale, because as we look forward, there's a large subset of applications where concurrency and parallelism are not necessarily as important, or their concurrency and parallelism of a scale that's relatively moderate. And we see a large trend of those applications moving toward cloud-based data centers or cloud-based use cases. And really that's the best place for many of those applications. But there is a significant number of applications for which concurrency, both at the processor level, the programming level, and at the system level, where concurrency is really important, and really you need to have an architecture that's adapted to the application. And that's the centerpiece of what Cray does. So our vision is really to build world-class environments for supercomputing that really are meant to map to a broad set of scientific applications in all sectors, whether it's government, commercial, and now analytics. And so we want to have that holistic system-wide view, and we want to project that forward. That's our view today. That's how we build systems today. The system that came out of the DARPA HPCS engagement is actually on track to be one of the most successful systems that Crays ever built. The XC30 supercomputing system was key to our success over the last 18 months and will continue to be the key to our success over the next few years. And that came out of an engagement with the US government, and really it's a tremendous success. People have often asked us when we were in the middle of the HPCS program with DARPA, is that going to be a success? Are we going to be able to have a production supercomputing system at the end of that? And I can, stand up here and say it's produced probably the best system that we've ever created. But we did it in a way that was flexible as we moved along that path. We continually asked ourselves, are we mapping to what the customers are needing, what the markets are needing, what the scientist and engineer is going to need as those systems were developed. Now, as we project forward to Exascale, this is a slide you've seen in one form or another 100 times. And so my goal here is not to show you slides you've already seen. But if you go back and you read some of the Exascale documents that people have been producing over the last few years, these four areas are always shown as the key point technology areas where innovation is needed. The issue, though, is, and I've seen this in a few of the more recent committees that have come out of Exascale, they're asking the question, okay, how does this map to productive systems, and how do they map to systems that are looked at the system-wide scale, not as a point technology? So these are typically, you'd see under here, a list of point technology issues where we need to innovate. And really, what's going to matter when you start building an Exascale system is how these different columns interact with one another. So for instance, you might find the most energy efficient processors, but they may not be the most resilient or reliable, and they may have big impacts on that. And a system-wide view of design is one in which you're going to have to overlay all of those point technologies across the pillars. So what Exascale is not, I think we'd all agree, it's not about peak numbers. It's not about pure arithmetic models. That's a point that Cray believes. It's not just about solving partial differential equations. It's not about embarrassingly parallel throughput. Again, there are other architectures for which we believe, although they may be exascale, when you talk about the sort of the number of computing elements, we don't view that as exascale from the Cray point of view, which is trying to get concurrency to work on a single problem or on a small set of problems. What can it be? Well, it can be a driver for innovation, both at the point technologies as we move along, but also in how those technologies map to one another. And it's really going to drive our innovation. It's going to drive our innovation in a number of ways. So if the goal is modeling the world or modeling these large problems where concurrency is really important, an area where Cray has a lot of experience. Our systems today are primarily used for solving mathematical models of one type or another. This is an area we know well. This is the area of the blue water systems. This is the area of Titan. This is the area of the hundreds of production supercomputers that we ship every year. Data models are becoming more prevalent, and data models involve taking massive quantities of data, doing search on that data, doing discovery on that data, helping to feed that data into analytic or mathematical models. So a prime example of this is in the oil and gas industry. About 10 years ago, everyone told Cray, you'll never get back into oil and gas. You'll never get back into the energy sector because they don't need networks. They can do things embarrassingly parallel. They can do things on the most price efficient, lowest performant networks in the world. Well, what happened is as sensors became much more sensitive, as the amount of data that an energy company could gather through seismic analysis become much larger and much larger, they started looking at much higher resolution algorithms for looking at and doing seismic analysis. And what this has done is it's caused a resurgence of algorithms that actually are very network intensive, that require a system design view of computation, not just a fast node with a cheap interconnect connected to it. And you're seeing today full wave inversion analyses that are using petascale systems on a regular basis. So we call this area data-intensive processing. And so this is really that blend of analytics and sensor data. It's that blend of computational and math modeling. And it's the virtuous cycle that begins to be produced. Now, you could just as easily apply this to social media. You could apply this to any number of areas when you're trying to do predictive simulations. And you want to map that to very large data sets. And so our approach has been to look at this as needing both computational needs, analytics needs, and in the center, in the hub of this wheel, data movement, data management, more intelligent storage. And these are the three areas that Cray sees as we look forward 10 years, that if you're going to provide an exascale system, you got to solve problems in those three areas and provide a complete system, soup to nuts. So in those three areas today we have technologies, I won't go through them, but basically we have both supercomputing and big data solutions in each of those areas today. Predicting what those look like in the future is going to be the challenge. So what makes Cray special with regard to trying to predict what these technologies will look like? Well, first of all, we have proprietary models that we've developed over the last 15 years. These are models that were developed initially for looking at designing vector processors. That was the first use case. And we'd use those models to build compilers. We'd use these to actually design the vector processors. Over the years, these evolved into internal Cray proprietary models that could simulate almost any processing technology available. These are the technologies that we initially decided to build the XK7 based on GPU technologies. We looked at those, we did simulations, very detailed simulations of how a real application would run in a situation where you have a GPU and you have it connected to a high-speed network. How are you going to optimize this global problem? It's not a point technology problem, It's a global system view of the problem. And really, now we map into that different memory models, and those are evolving as well as we move from just DDR memory to using NVRAM as either a storage device or as a memory device. It adds a whole set of layers into where the bottlenecks are and where they move, because those bottlenecks change, and they're going to change multiple times between now and the delivery of those first exascale systems. The next area is our experience with producing systems at scale in production. And what I really mean here is an exascale system is going to require someone to put together components that are very large, very quickly, test them, ship them, integrate them, and put them into production. And the faster you do that, the more production time. Every day you lose as you're building an exascale system is billions of concurrent cycle hours you're losing. So when we put together the Blue Water system, we actually got the order in November of 2010, 2011. November of 2011, and by the middle of 2012, by June of 2012, we had actually delivered 300 cabinets of the largest general purpose system in the world. 300 cabinets, 20 petaflops of storage. And that type of production view of systems. And then the ability that it's not just a one-off. This is something that we're shipping basically all around the world every day. Those lessons learned are going to be critical with looking at how you actually put together and the logistics of building an exascale system. And then finally, Crays really focused on customer-centric metrics. So today we have metrics that analyze power consumption on a per processor basis as jobs are running on our systems. On the XE30s, we can tell you how much power you're using as you run any given application. We can make sure that the TCO today is of value to you. Are you getting the most out of your electrical budget? But that's because our design points are really about sustained application performance. They're not about peak in any sense of the word, whether it's peak network bandwidth, peak I/O bandwidth, peak computational. It's all about sustain and what are the bottlenecks. One of the things we did with our storage appliance, the Synexion, was we made sure that the design metric allowed for you to get the most out of every spinning disk that you have in that design. A typical spinning disk parallel file system gets somewhere between 20 and 50 megabytes per second per spinning disk spindle. And if you're going to design an exascale system, you don't want that, because that's only 30% of the capability of a disk drive. You need to have something that's aiming at 100 to 125 megabytes per second per spinning disk, or else you've pushed the bottleneck out. And that's really the design philosophy we have, and it's really about those bottlenecks for sustained performance. So how do you build an exascale system? Well, here are my little cartoons that I made. So really, traditionally it's about best-of-breed technologies. You'd have a best-of-breed network. You'd have some type of compute node that's best-of-breed technologies. You just pack tens of thousands of those behind the network. Perhaps you have two types of compute nodes or multiple types of compute nodes, some specialized nodes either for I/O or for some type of high concurrency or for larger memory. Used to be that these were two separate design points. Looking forward to 2020, I think it's clear that because of integrated circuit technology, that some of the technologies from the network are going to really mesh together with the CPU technologies. And what it's going to boil down to on these is really how you do the software around it, how you do the resiliency around the system. And you got to have that system view of the network and CPU. Typically there's an I/O fabric of some type, and looking forward 10 years, we're going to have some competing technologies there. I think we've got some great I/O network technologies today. Those are going to continue to evolve. Ethernet's going to become more and more competitive in the I/O technology space. InfiniBand is continuing to be the leader, really a network designed for I/O technology, and one that is really excellently handles excellently most of most of the I/O that we do at the highest scale. In fact, it's the IB is the infrastructure that we believe today is the best of breed. We hardly ever ship an Ethernet-based I/O just because of that creates a bottleneck in our systems that we'd prefer to avoid. But that may change. 10 years is a long time for that to change. And then you back this with the parallel file system. And the parallel file system, the dynamics there are going to change quite a bit. Disk drives are going to become larger, but that's driving real innovation, real movement of bottlenecks. Today, well, it used to be a couple years ago an MD RAID. I think Mark mentioned MD RAID earlier. MD RAID would handle, you'd have 8 disks, basically 8 plus 2 MD RAID. You basically can do a rebuild on a few hundred megabyte drive pretty quickly, so if a disk fails, you're in a reasonable shape. As we move towards software-based RAID technologies, you're able to spread the RAID across many more disks, and you're able to kind of hide the rebuild times. But the problem is, the more disks you spread software RAID across, the more likely you're going to get more than one disk failure, and so then you're going to have a balance point. It's going to be really tricky, especially if you get up to 4, 5, 6 terabyte drives, to know where the balance point is for that crossover between a really good software RAID and conventional MD RAIDs or hardware RAIDs. So that's going to be a tricky balance point over the next few years. One clear thing that we're seeing is that the bandwidths of these conventional spinning disk systems is not really increasing very dramatically. We delivered the first terabyte per second file system. In fact, we just ran a benchmark on the system a couple weeks ago, and it was 50% full, still running in the optimal settings at over a terabyte a second. Things were working pretty well. And a few other terabyte per second file systems have been delivered with somewhere between 20 and 30 petabytes. But we're not seeing 5 terabyte per second file system. So there are real constraints here. And what we're seeing though is that people are trying to look at those constraints that the spinning disk has, and they're throwing in solid state in various ways. So whether it's NVRAM or SSDs, there are competing technologies, whether that should actually be incorporated on each of the disks as a caching layer, or do you keep it separate as a file system? And so there's going to be a lot of questions around where to put the bottlenecks in this kind of design. Now you notice I didn't draw any lines. I didn't draw any lines there because, in fact, those things could be close to the compute, or they can be close to the file system, or they can be in both locations. So that's why I chose to kind of put them there, sandwiched between the compute and the file system. And I think we're going to see a lot of innovation here. It can drive high IOPS, it can drive high bandwidth. We're probably going to see a turnover somewhere around the end of the decade where the price per performance and the price per gigabyte is going to cross over with spinning disks, or at least some spinning disk technologies. So I think you're going to see a growth of the use of these SSDs, but they bring challenges of their own. One of the big challenges is if you're going to put those close to the compute, are you going to treat them more as memory, or are you going to treat them more as cache, or are you going to treat them more as a file system? It's really going to put a lot of pressure on the software that we layer around these technologies. I've actually not said anything about software here, but it's implicit. If you have a system view, you got to worry about, are you open? Are you talking to the rest of the world in an open fashion? Are you using file systems that can be shared? Are you using open programming models like we just heard? So Cray's looking at all those things. We've been involved in the open, many of the open standards for the programming models. We're innovating on Chapel, which is a programming model that's open as well for the PGAS. I think it's going to be critical that this whole thing be wrapped as they said in the Exascale reports that I've been reading, in a productive, open system that can talk to the rest of the world. Otherwise, you're just building something for one customer. So Cray, our view is, there are the big government customers. You want to build that for those customers. You also want to build it for your weather and climate customers, and maybe they need a lot more spinning disk and a lot less solid state. You've got your big energy customers, you got your manufacturing, you got your media and analytics. Cray's philosophy is to design to the scale. to exascale. That is going to be our design point, just the way today is designed to 100 petaflops. And then to bring those technologies down. And so really, it's all about designing the highest scale, design to the greatest resiliency to build that exascale system, get that power efficiency, utilize the best of breed technologies, but then scale those down. Because many in this room, you're not necessarily going to be accessing those massive exascale systems. You're going to be accessing a system at the University of California, or you're going to be accessing a system at Stanford or elsewhere, and you really need to drive these technologies down. If exascale can't solve this problem, we got to ask why we're doing it. So it's got to be able to scale technologies down. Maybe not to the desktop, but at least to what I would call the university level or departmental level. It's got to enable a broad set of applications, both the traditional compute and the analytics and big data. It's got to drive high ops and a high bandwidth. And really, that's what Cray is doing to position for exascale, and that's where our vision is. Thank you.